Hawksworth. Thank you guys for attending the SEMA Emerging Trends and Technology Network Virtual Education Series. ETTN's Education Committee has been hard at work to provide additional resources for our members and enhance their technical knowledge of the industry. Be sure to check out all of our series on the SEMA educational site. Nicole will add to the link in our chat today, as well as a follow-up email. So my name is Jake Hawksworth. I am from Hypercraft, and we specialize in all kinds of things in EV, but one of the things that we do is battery design, development, manufacturing. So I have recorded today's session already, and I'm going to start that in a few seconds. While the recording is playing, I'll be on the chat, so feel free to have any questions. Toss in any thoughts as you have them. I'll be able to respond via chat, and I'll also be available after the recording ends live on video to answer questions that you might have. So let's get started, and we will start the video. Hi, my name is Jacob Hawksworth from Hypercraft, and I'm very excited to be discussing battery pack design basics today as part of SEMA's virtual education. So we are going to jump right into it. And this is essentially the agenda for what we have planned, which is kind of a general intro and basics about battery packs, their architecture, and then finishing up with a group discussion. By the end of the presentation, I hope that you'll have a basic understanding of a lot of the components and the general design concepts that go into battery pack design, the cell types, high voltage and low voltage pack architecture, the cooling designs, and power distribution, which we'll get into. So I want to start by discussing a little bit about the terminology. And throughout this presentation, we are going to be covering these terms much more frequently. And so there will be this kind of repetition. And if you're not familiar with them already, this will be just kind of a good understanding of the basic terms that we use in battery pack design. So the first thing to kind of cover here, again, everybody will have access to this information so that they can go back and reference it at a later time. But the first term that I want to cover is C rating. So the most important part of a battery pack are the cells inside. And the C rating is that measurement of current that allows a battery cell to be charged or discharged at a certain rating. And we typically see cells from manufacturers rated by constant and peak current. And the amp hour capacity of each cell times its constant or its peak C rating gives you that cell's ability to discharge or charge at that rate. So we'll get into the math of that a little bit later. Amp hour, which is the unit of electrical charge, multiplied by time. So it is not only just amps, but it's also a reference of time. That's something that we see every cell and pack or module rated at, which is amp hours. Kilowatt hours is the unit of energy measured in time. So this is kind of going to be our standard overall capacity. If you look at electric cars today, the most common term that we see is what's its kilowatt hour capacity. And that gives us a real sense of how much energy is stored in that pack, providing us with a way to understand, depending on how we discharge or we use that power, how long that pack will be in use. So the BMS, the battery management system, is in charge of controlling the charging, the discharging of cells, monitoring temperatures and things like that. We'll dig a lot deeper. High voltage interlock. We're not going to talk too much about high voltage interlock because it's a term that's used, throughout an electric powertrain system. But it is relative to the battery pack in the sense that A proper battery pack design for high voltage systems should have an HVIL, or a high voltage interlock. And we'll kind of talk a little bit about that in power distribution. Energy density is the amount of energy that can be stored in space. So it's a common term that we look at, which is watt hours per kilogram, that gives us a sense of how much energy is stored in an amount of space and within a certain amount of weight. There are two ways that we rate cells, which are energy cells and power cells. Energy dense cells have energy densities usually above 250 watt hours per kilogram. And power cells, we typically see at this time with current technology, power cells having less than 250 watt hours per kilogram. But power density is the measure of power units or output per unit volume. So it's going to be a different metric, but it tells us really how much power is available to us within a cell or a module or a pack. The volumetric density is really more about the size and the mass density. So it's also known as specific mass, and it's a little bit less of a term that is common, but for a lot of battery pack design, volumetric density is considered. So what is a battery pack? What makes the battery pack? And this is something that, really needs to be understood, because in today's world, where we talk a lot about batteries, just as a general term, there are many different ways to look at it. And this is how we would define a battery pack. And I don't think that there's really, a technical way to look at this. This is just how we see a battery pack, is that a battery pack typically has more than one cell. It is a combination of cells that achieves, essentially a certain capacity in kilowatt hours, a certain amperage capacity in amp hours, and a specific voltage for a system. So it has those three defined elements to it and is typically made of more than one cell. The other thing that we look at that defines a pack is power distribution. A battery pack without power distribution is a module, and therefore not a battery pack. Power distribution is the way for energy to flow safely in and out of the pack that can be managed and integrated into the rest of a working system like an electric powertrain. Essentially, battery packs are just DC power storage, but there's always an end use in how the battery pack is used. There are different types of battery packs in applications like ESS, or energy storage systems, that are stationary for solar or battery backups, and different things like that. This presentation is really much more focused around battery packs in use of traction applications or vehicle applications. So the power distribution design, or the way that energy can flow out of the pack and be used in a system, is very, very essential. And without it, it is a module and not a pack. The third thing that would define a pack is its enclosure. Enclosures, which we'll kind of get into towards the end, serve many, many different functions. So there's some of the basic ones of protecting the internal components from damage from kind of the outside elements, as well as protecting the vehicle and the users from the internals, which is the high voltage and the high current. But from my perspective, these are kind of the three fundamental core elements of a battery pack system. So the pack construction basics, and I've used these terms already, but I want to dig a little bit deeper on the construction architecture. So at the fundamental level, batteries are made up of cells, and it's the smallest unit of a battery, and it includes, typically, depending on the technology, these four key components, which is the cathode, the anode, the electrolyte, and the separator. Now, this discussion is really not about battery cell technology or construction. It's really about the pack. So we're just kind of going to leave it very simply at that the cell is the smallest unit within a battery pack. And from there, we use the combination of cells to build either modules or the battery pack. So the second kind of level inside of a battery pack is a module. And so battery packs don't have to have modules, but a module is a great way to break up a large pack with high voltage into smaller sections that are easier to work with. They're easier to handle and load into a battery pack during construction, and they're easier to use as a building block for different battery packs. If you have one module, they can be configured differently, and then they can be built into battery packs. So essentially, they're built a lot like a battery pack, and a battery pack can be made up of only cells without modules. But modules, besides having a protective enclosure and power distribution, they're very similar to packs, just smaller units. And a pack, as we've defined, is a group of cells or modules that creates a specific voltage or amp hour capacity and includes the enclosure and power distribution in it. So within the batteries, when we look at designing a battery pack, there's three primary different types of cells that can be chosen today. And we're going to start with cylindrical, but there's cylindrical, there's pouch, and there's prismatic. And this image shows all three. So there's a reference to what they look like. But cylindrical, which are used in things, cars like Teslas, are very popular in electric vehicles. They have a huge range of chemistry options. They have a small form factor, so they're very easy to configure into different shapes. On the Pro side, that small form factor, does allow creating all these very unique different shapes out of battery packs. So they don't have to be rectangular. The battery pack can be made into a large cylinder. They can be made into all these odd shapes to fit into many different spaces. Cylindrical cells also come in very, very standardized sizes. So the two primary sizes are 18650 and 21700s. The way that they're rated in an 18650 is that the diameter of the cell comes first in the number. So 18 represents 18 millimeters. And then the second two digits represent the length of the cell. So 65 is 65 millimeters. So the same would be for 21700, 21 millimeters in diameter and 70 millimeters in length. There are also many other new sizes that in the industry we're starting to see, but the 18650s and the 21700s are very, very popular. And they come in many different chemistries, including one of the more popular, which is NMC. They also provide many different ways for cooling. And we'll talk a little bit more in the future about the cooling designs, but they end up being a very popular choice for many applications. The cons are because they are round, they don't package as tightly. So you can see packs that have a little bit lower energy density than sometimes prismatic or pouch cells, which is also very chemistry dependent. The way that you connect cells within a pack for cylindrical, typically requires some type of equipment and are much more geared towards automation or high volume manufacturing as opposed to low volume customized battery packs. And the third con to cylindrical is their cost. Cylindrical cells, because each cell is small and has its own metal casing to it, they tend to be more expensive. They have lower amp hour capacities to them, and so you need much more cells in a pack to equal the same total capacity. The next cell, which is on the right-hand side, is prismatic, which are rectangular in shape, typically have threaded busbar connections, and they have a structural shell to them. So a lot like cylindrical, they have some type of structure that protects the internals of the cell. And the pros to them is that they're very easy to use, which the threaded busbar connections are part of why it's very, very easy to use. Doesn't require any type of welding. They are very durable, like cylindrical cells, because they have some type of protection to them. And they come in many different chemistry types. The cons is that they are heavier because they have a structural outer shell, and they have a large form factor with typically large amp hour capacities. So developing smaller packs and high voltage can be a challenge. They typically, end up being much larger battery pack capacities, at least 40 kilowatt hours, depending on voltage, or higher. The third type is a pouch cell. So like prismatics, pouches are rectangular in shape, but they don't have a structural outer shell. They are flexible, and all the internals are contained in a foil pouch. So they typically have tabs for the positive and negative attachment, and which requires some different types of cell bonding, typically laser bonding or laser welding the tabs together. But the benefits to a pouch cell is that they're very high energy density. They can be packed very, very tightly. They come in many different chemistries. They are smaller in form factor, but have large amp hour capacities. So typically build very high energy dense battery packs. And they are also typically less expensive, and there's less cells needed. The cons is that they are less durable because of the form factor. They're much more susceptible to deformation under high loads, mismanagement. They're difficult to cool because it's typically harder to design a cooling system that pulls the heat out of them. They're because of the mass density, and they can be more challenging to integrate into a battery pack. Pouch shells, when designed into battery packs in low volume or custom applications, are typically used in modules, and those modules are easier to integrate into a complete pack. So cell chemistries, and we're spending a little bit of time talking about cells because cells are very fundamental to having a battery pack that meets the application and performs the way that you would expect it to. And so, and all of this is researchable, so we won't go too deep into cell chemistries. But I think the main thing to understand here about cell chemistries is that the way that battery manufacturers design cells is typically around, having high power density, or high energy density. There are some hybrid cell chemistries that kind of combine as best as they can the benefits of energy density and the power density. But typically you're going to pick a cell chemistry that by its rating delivers a high amount of power for high power applications or performance applications, or for applications where range is the primary objective. You pick a cell type or chemistry that has a high energy density. So kind of like digging a little bit deeper on like, whether or not the battery pack is going to be used as an energy pack or a power pack, and ultimately defined by if the cell is a power cell or an energy cell. These are kind of some basic metrics that can be looked at to define. Now, the holy grail is to have a cell that is both power dense and energy dense. And in the future, those chemistries will be much more available, or those cell technologies, whether it's carbon battery, graphene-based carbon battery cells that utilize electrostatic technology like ultracapacitors, or it's a new lithium chemistry like lithium sulfur that provide significantly higher energy densities without sacrificing power or discharge. But with the current technology that we have today, this is typically what we see in a power cell versus an energy cell. So a power cell will have a 3C continuous or more rating with a 6C or more peak. And again, the C rating is just the discharge rating of the cell. So the 3 and the 6 would be multiples of its amp hour capacity. If it's a 50 amp hour capacity, the continuous discharge would be 150 amps, and the peak would be 300 amps. So it also typically has lower energy density, like we discussed, which typically you see right around 120 to 200 watt hours per kilogram. And lower volumetric density, which means that to have the same capacity, a power cell will take much more space, volumetric space. The battery pack will be in 80 kilowatt hours, will be much bigger in physical size than an energy cell will with the higher energy density and a higher volumetric density. So energy cells, which are not typically okay for high performance applications, have around a 1C continuous rating and a 3C peak. The hybrid cells that kind of balance the benefits of both, which we would see in something like Tesla would use, is a 2C continuous and a 5C peak. And so at larger capacities, they do have enough current discharge for higher performance applications. And we'll get into some of the calculations later, because one of the core fundamental elements of designing a battery pack is identifying the cell to be used and doing all the calculations so that you know how many cells in the series and parallel configuration. So we're going to talk a little bit about applications for battery packs in the automotive industry. And essentially, they're broken down into 3 different types of vehicle platforms, which is a BEV or battery electric vehicle, HEV, which is hybrid electric vehicle, or PHEV, which is a plug-in hybrid. We've had hybrids, in the industry for quite a long time, and there's many different ways to integrate battery or electric storage into hybrid vehicles. BEVs or complete battery electric vehicles, or kind of starting with Tesla and now some of the other automotive manufacturers, are kind of the newer thing. They require the battery packs require a much more advanced system, because the vehicle relies completely 100% on the battery pack, and a lot of times there's a very delicate balance between power and energy density, depending on the use and in the vehicle platform. But they have the most advanced battery management systems, cooling systems, power distribution for the vehicle, and they're responsible for powering everything in the vehicle at the chassis and the body level, including the powertrain. So not only the motors, but also they provide 12-volt power through a DC to DC converter. so that the vehicle has 12-volt power for all chassis systems and also body systems like electric windows and stereo and other things like that. So the most complex and advanced battery packs are definitely in the BEV area. Hybrid electric vehicles usually have the smallest battery pack in form factor and are much more going to be designed around power density, because the only way that they recharge is through the vehicle's primary powertrain system or combustion engine. They rely on regenerative energy through braking and other systems on the vehicle to regenerate while the vehicle is in motion, and then provide power for accelerating or hybrid power to extend range. So again, there's many different configurations on hybrid electric vehicles, but the main difference between them and plug-in hybrid vehicles is that plug-ins have a charging system to the battery pack, which is typically kind of the medium size between a battery electric vehicle and a hybrid electric vehicle, are able to be charged offline, separate from regenerative braking or other regenerative methods. So a lot like a BEV, the plug-in hybrids, depending on the application and type of vehicle, are much more commonly energy dense, but have a little bit more blend between energy density and power density. So within a vehicle platform, there's a couple different configurations to a battery pack. And as long as the battery pack meets the primary specifications that we defined at the beginning of the presentation, which is it's a group of cells, it has integrated power distribution and an enclosure. There's a couple different ways that battery packs can be used. So they can be designed as an all-in-one single battery pack within the vehicle system. So the skateboard deck concept typically applies here, where it's one large battery pack that houses all of the power distribution for the battery system, all the cooling, the battery management, and everything in one single enclosure. This is a great way to reduce cost and weight, and also provide potentially added benefits of stress member integration, where the battery pack can be used as a structural member of the chassis to save weight on the whole vehicle platform. The downside of the single battery pack, depending on capacity, is that it is very, very large. And for existing vehicle platforms or vehicle types that need some flexibility or optimizing the battery packs or the cells in many different locations on the vehicle, a single battery pack can be really hard to use. So packs can be grouped into battery pack groupings. So they typically are connected in series. There's many reasons why it's typically very unsafe to do parallel pack groupings, but typically the packs are designed in lower voltages and then connected together in series to build higher overall battery pack capacities. So the benefit to this is that they can be placed in different places on a vehicle platform and optimize space, spread out the weight. And so for like vehicle conversions, a lot of times this is what we would see. Kind of a bad example, which is not a battery pack grouping, it's a module grouping, is how people, in the aftermarket automotive industry might take a battery pack apart, a Tesla battery pack apart, take the modules out, space the modules out across the vehicle platform, fitting them in different places. There's typically, like from a Tesla Model S is about a 5.3 kilowatt hour capacity, and it's 22 nominal volts. So lower voltage, and they're placed throughout the vehicle and then connected together to provide the total capacity and the total nominal voltage of a 400 volt system. In this example, it's a very, very bad idea to do what I just described. It's much better to do a battery pack grouping instead of a module grouping this way, because the modules, the way people use them, don't have any proper power distribution, and they are very, very unsafe. And so those 5.3 kilowatt hours, if in an enclosure with proper power distribution and then connected together, could provide a very safe, properly designed pack grouping. But you know, kind of the reason to cover it is because with a proper design, you know, it doesn't need to be one single battery pack. The battery packs can be broken up into smaller subsections, and it provides also the benefits of you know, easily being able to be removed or serviced, so that, you know, whereas one single battery pack can weigh, you know, 1,000 to 2,000 pounds, battery pack groupings can be much easier to manage, to be installed or serviced or removed and replaced. And for high performance racing applications, there can be hot swappable pack designs that can come from battery pack groupings, etc. So just relative to the overall design, you know, there's no limitation to you know, how they're configured, but there are some fundamental things that need to be considered. So this is kind of just a very simple process, step-by-step process of kind of how to approach designing a battery pack. And again, this presentation is not designed to educate you or equip you to design a battery pack, as much as it is to just cover the basics so that you have an understanding of what goes into a battery pack. Properly engineered and designed battery packs take extensive development and engineering, and as well as testing to make sure that they are good for the application, and they are safe for use in a vehicle platform. But this is kind of a simple, logical approach to how you would design a battery pack, which is step one: define the pack specifications on paper and identify the cell or module to be used. So we're going to walk through the math on this shortly, but essentially the goal here is to start with a general understanding of the needs, so that you can list out specifications and base the whole battery pack on those specifications. So once a cell or module being used to build the pack is identified, then you can calculate the cells needed and create a configuration of series and parallel between the modules or the cells. There are many factors to this, including considering the cooling system integration and the BMS, but this is a very essential step because it will tell you how many cells are needed, and therefore a space claim, and the rest of the components can be designed together and then an enclosure at the end. So the next step is to decide on a method for connecting the cells, and this is very cell dependent. So if you're using a prismatic cell where you can bolt bus bars together, then you're going to use a bolted bus bar configuration. If you're pouch, you're probably going to be using laser welding. And if you're building in small volume and cylindrical cells are being used, then you're most likely going to be tab welding the cells together. But once you know how many cells and what cell you're using, this is a very important next thing to decide. The next thing is designing the BMS architecture. So we will get into the different types of BMS architectures, but the BMS and the integration into the battery pack is very critical. There is space required for the BMS system as well as wiring routings and where the BMS is attached to series strings, which again we'll get into as we kind of talk a little bit more about BMS. Sizing the cooling system will be, fundamentally based on the performance side of the pack and the types of cells used, and we'll cover some cooling system designs next, and then you'll design the power distribution, and then in the final step, you will be able to design and build the enclosure. So that's, essentially just a very logical approach to designing a pack. So connecting the cells is something that takes a lot of development and testing, but these are kind of the most popular ways to do it. One, like I mentioned with prismatic bolted bus bars, make for a very simple and easy way to connect prismatic cells together. Laser welding, which is typically used on pouch cells, welds the tabs, the pouch cell tabs together. Tab welding is something used on cylindrical cells as wire bonding and compression. But tab welding is really good in low volume applications where wire bonding is typically automated and requires some significant equipment to achieve. Wire bonding also has the added benefit of fusible linking cells to the primary bus bars or collector plates, and reducing cost. Compression connections are much less popular and can be very, very tricky to design. But the best example of a compression system is like what you'd have in a TV remote, where there's a spring that applies pressure connecting the negative and positive, leads to a battery cell. So these compression systems can be much more advanced and are being used in some automotive applications, but they're something that take a lot of design and development and testing to prove out. So the BMS system within a battery pack is one of the more critical parts of a battery pack. And it is critical because of safety and proper use of the cell within the system. It's something that kind of serves these primary functions, but there's many different design concepts. There's a lot of proprietary technology used by companies, but there are some great automotive aftermarket applications, including, for example, AEM has a BMS system that integrates into their VCU that is much easier to use and user-friendly. So just kind of talking about their primary functions that they serve, which is monitoring cell current and cell voltage, providing cell balancing, and in the way that it does that in cell balancing or active cell balancing is by providing a heat sink to lower the delta of voltage difference between cells within the battery pack. And then it monitors cell temperatures so that it provides live feedback to the overall system to tell if the cells are being work too hard, or they're too high in temperature or too low in temperature for charging in cold weather applications. So ultimately, the BMS provides really important information to the whole system to provide thermal conditioning and safe charge and discharge of the cells. So the three different types of BMSs that exist are centralized, which is basically this concept of a single BMS controller that's connected. It does create a huge amount of wiring within a battery pack system. And I encourage everybody to go a little bit deeper. If you're sizing a BMS or selecting a BMS for a battery pack system, there's a lot of research that needs to be done that integrates into how you're designing the battery pack. So this is just a very high level view. And then there's distributed, which sometimes in certain variations could also be called decentralized. But distributed is a cleaner but much more expensive way to integrate a BMS, where every cell or cell series string has a BMS board connected to it. And so if you can imagine, in a 400 volt system, which is about 352 nominal volts for a 3.7 volt cell, there's about 96 series strings. So there'd be 96 BMS boards connected to each cell or series string that would communicate to a main controller. And then modular, which is kind of a mix of both, which is a BMS, sometimes called a satellite or board, that can handle up to sometimes 18, depending on the BMS, 18 series strings. And then it combines all the data from those 18 series strings and passes it to a master or a main controller. So a modular BMS system provides kind of that higher simplicity and lower cost, and is a good choice for many applications. So we're going to move really quickly through cooling systems, but I want to cover that there are passive systems which are not actively monitored, but are sized to discharge heat and keep the cells cool, but it is not an intelligent system, and they can be air or water cooled. And then there's active cooling systems, which are much more typically liquid cooled or liquid submersive cooled systems. And they provide through the BMS active information to the cooling system to monitor the cooling. So chilled liquid cooled systems for battery packs that would require much more detailed information on temperature. So in passive systems, they're typically heat sinked or cooling. There are some very high performance, including something Lexus is doing, where they are air cooled in high performance. So they're able to remove a significant amount of heat through air cooling. But typically we see motorcycle or lower voltage applications with, fins, cooling fins to pull the heat away from the cells and discharge them out into the air. Chiller plates are one of the more user-friendly and easier things to design or fabricate. They do not have a very significant way of pulling heat out of cells, because they are touching one surface or one face of cells. But chiller plates can be a very good way to do a battery pack design at lower cost. Phase change material, which is becoming somewhat more popular, relies on a material, wax-like material, that changes phases when it's heated. So as it changes phases, it absorbs the energy and removes the heat in the process. And so these, eliminate a lot of thermal propagation between cells. So cells heating up other cells, which leads to thermal runaway scenarios. But phase change materials are very expensive and, are typically not as popular in automotive applications. Immersive or submersive cooling is a design where the cells are actually submerged in a dielectric fluid absorbing the heat of the cells. This has become very, very popular, and there are companies that provide this as a solution in modules or complete packs, because this is a way to get a cooling fluid to have 100% contact to the cell. And they're typically a higher weight, higher cost, and higher complexity, but they are very, very effective cooling systems. So kind of getting into cell architecture and the way that battery packs are sized. This is some very important math to step one, designing a battery pack, which is taking these three very specific ratings, which is amp hours, cell voltage, and watt hours, or in higher capacities, kilowatt hours, and calculating the overall specifications of a battery pack. So in this simple example, we have a 100 amp hour cell or parallel grouping of cells that provides 100 amp hours and a pack voltage of 350 volts, providing a total capacity of 35 kilowatt hours. So before you're able to design a battery pack, you have to consider what the system voltage is going to be, either through a single pack or a pack grouping, and what cells specifically are being used, or the modules and the capacity of that, to define your desired overall capacity. So before we get into an example of kind of specifying a pack and doing the math, there's one last thing that we need to cover, which is series and parallel connections. Now, many people are going to be very familiar with this, and it can happen at the cell level or the module level. But the way that cells are combined in series or parallel has a huge impact on the voltage and the amp hour capacity, ultimately the overall energy capacity of a battery pack. So series connections are multiplying voltage, and they connect the negative to the positive terminals, keeping the amp hours the same. So kind of in this simple configuration, current is flowing through the cells as they're connected, negative to positive, negative to positive. Parallel connections do the opposite. They multiply amp hours and connect the common polarity terminals, keeping the voltage the same. So in this scenario, current flows through the pack where cells positive to positive and negative to negative. So a great way, if you're not familiar with this process, to size or define the pack is to kind of start with a couple notes. So in a typical electric vehicle today, complete electric vehicle, it's most commonly a 400 volt system or 350 volts nominal, and an 80 kilowatt hour capacity gives you, somewhere between 200 and 300 miles of range. So step one, defining the cell. For this example, we're going to use a Samsung INR 40T, which is a great, kind of blend between power and energy. But it is considered a power cell. It has a 4 amp hour capacity at 3.7 volts nominal, and the peak voltage of the cell that it'll charge to is 4.2. So for this example, we're going to use nominal voltage in the calculation. So step two, defining the series strings to define the nominal pack voltage, which is an automotive industry standard for 400 volt systems when using 3.7 volt nominal cells, is 96 cells in series. So this is just a good thing to remember if you're building a battery pack, and it's going to be a 400 volt system. It's 96 cells in series. So we have a 96 series strings, and then step three is kind of reversing our initial formula because we have a known system voltage, and a known kilowatt hour capacity that we're going for. So what we need is the amp hours of the pack. So we're going to divide the 80,000 watt hours or 80 kilowatt hours by 350 nominal volts, which is going to give us 227 amp hours. That's what we're needing. So step four, take those amp hours, the 227 amp hours of the total pack capacity, and divide by our cell amp hour rating, which is 4 amp hours, to define our parallel groups. So 227 roughly divided by 4, the closest kind of even number is 56. So we're going to have 56 cells in parallel and 96 cells in series. So step 5 is, which we're really trying to get after, or the information we're really trying to get from this exercise is how many cells are needed for this pack and what the configuration of those cells in series and parallels would be to provide 400 volts and 80 kilowatt hours capacity, is to multiply the parallel groups by the series strings and calculate total cell count. So that's 56 by 96, providing 5,376 cells in a 56 parallel 96 series configuration. So kind of the next step, now that we have the type of cell and the amount of cells needed for the pack, is to look at what the final total performance of the pack is going to be. So an INR 40T cell, thermally managed, has a 3C continuous and a 10C peak. And so if we do the math on that, what we get is a 400 volt system or 300 volt nominal pack that has a total of 224 amp hour capacity and a 80 kilowatt hour energy capacity. That provides a continuous discharge of capability of 672 amps and a peak discharge, which the tendency to peak is, I believe, about 10 seconds of peak discharge at just over 2200 amps, which is a huge amount of current. So the next step with this given information and total pack performance with this cell is to design the rest of this system, which is the cooling system, the BMS architecture, and the power distribution. Power distribution, to dig a little bit deeper on what power distribution is the ability to get the power, the energy stored inside, out of the pack, outside the enclosure, and doing it in a very safe way. So because of the variety of applications, pack designs, uses, there's many different strategies available to do this properly. But here are some kind of basic things to consider, is that besides all of your cell-to-cell connections between your parallel and series strings inside your parallel groups and your series strings inside the battery pack, all of the current will be collected into a bus bar and connected to something that provides a way for the current to get out of the pack. Accumulating all of this current into one connector or one bus bar that connects to that connector requires proper engineering, which is based on cross-sectional area of the bus bar. So depending on the current, there are calculations that need to be made, which is a little bit too deep for this presentation, but there's calculations that need to be made that say that the bus bars will handle that level of current. The other part of power distribution that provides safety and control is on high voltage packs. There should be a contactor, typically a negative contactor, inside the back that is externally controlled, that closes, allowing current to flow. And when not being used or there's an unsafe condition, the contactor can open, eliminating live current at the connector. There should also be a fuse inside a high voltage fuse that's rated for pack voltage in amps that's inside the battery pack, so that if there is any a problem externally from the pack, the fuse can blow and protect the pack, its contents, and externally the vehicle and its users. So earlier in our definitions, we talked about HVIL or HVIL, which is high voltage interlock. And that the high voltage interlock is a low voltage circuit that runs through all the components in a high voltage system and provides many different ways to interrupt that circuit to tell the system that is unsafe, where the contactor can close and you can prevent high voltage from being available at the contactor or at the connectors. So some connectors, such as Amphenol, have high voltage interlock wiring integrated into the connector, which is highly recommended, so that when the connector is plugged in properly, the system knows that there is a safe connection. When it's unplugged, the system knows that there is no connector, and the high voltage contactor will not open, keeping the current from being at the connector. So you have a non-live pack. So there's a lot more to power distribution, proper engineering, but just kind of for high level understanding, there is a lot of design and engineering that goes into power distribution from a pack side. So the enclosure, which is kind of the final step of a battery pack design, and here's one that has been designed by Hypercraft. which is about 10 kilowatt hours. And you can see there are many features to it. So the enclosure is meant to protect the internal components, as well as protecting externally against access to high voltage, to keep high voltage contained and all the current contained within the pack and the energy stored within the pack safely. A proper enclosure can provide fire protection for the vehicle in case of a thermal runaway or any type of fire or impact. They provide a way to structurally mount the pack safely within a vehicle platform, and an interface for all the power distribution, cooling lines, and sometimes even features that show state of charge. And those things such as state of charge or any CAN communication is a critical communication interface. And then also, as mentioned earlier in the presentation, they can provide stress member integration into the vehicle platform. So there are many ways to design the system, the pack enclosure, and there's many different materials that can be used. So that steel, metals like steel, aluminum, as well as composites, and in some cases very very high performance plastics. But the application and the use is the most important thing to identify before doing an enclosure design. Overall, the most important thing to understand is to be safe. A battery pack design, development, and assembly is essentially the most dangerous part of a high voltage system. This is where high voltage exists and high current exists. So any other part of a high voltage system or an electric vehicle usually does not have live current, or should not, while you're working on it, designing it, should not have live current. Where the battery pack, as you're designing and building and assembling the battery pack, there is current and electricity. So have the proper safety and high voltage training, and understand at a much deeper level than even this presentation, the design and proper engineering of the battery pack system before attempting. Hopefully this has been very insightful to what goes into kind of the basics of battery pack design, and definitely appreciate your participation and would love to hear your questions and comments at any time. So here's some contact information, and we appreciate your time. Thank you very much. Okay, so that was the end of the presentation, and happy to take some questions, comments, or just kind of have an open conversation with anybody who's interested about anything relative to battery packs or EV applications.
Do you want me to read them off to you? Would that be easier?
Yeah, you could if you want. I see it now, so I can actually read this one aloud. So this question is about, do these vehicles all have an auxiliary battery? If so, are they different chemistry than lead acid? And what is their primary purpose? How can you test auxiliary batteries? So, most of what we kind of covered today relative to battery packs are not lead acid. They're different types of lithium batteries, including like NMC, and variations of that. So there's a lot to that, but these are more energy dense and batteries that are specifically designed to be used in battery packs. So relative to an auxiliary battery pack, like in a hybrid situation, like these are not used as battery starters or anything. These are actually battery packs used for propulsion systems, and so that's typically kind of what we covered today. So kind of another question, can this type of design be used for 12-volt batteries as well? Absolutely. So, just like everything kind of within what we talked about, series and parallel connections, you can take any cell and connect it in series and parallel to get, your amps and volts. So, it's just really chemistry dependent. Lead acid batteries or specific types of lithium cells chemistries have much more like much higher amps potentially, so they're better for starting. Most EV specific batteries are higher in energy density, and so they discharge constant current instead of like starting current or high power discharge. So another question regarding the useful temperature range considerations and any danger zones. So, and I'll answer that at the pack level, because ultimately a well-engineered battery pack is designed for the temperature range that it's in, which is usually a much higher range than the cell itself. So thermal conditioning is like even expanding beyond cooling. There's also the heating side. Allows cells individually within a pack to be used in much more harsh environments. So in high temperature extremes such as heat in the desert, or very cold temperatures. So that thermal conditioning and a proper BMS integration will monitor the cell temp. And there's a lot of modeling. So this is like control system, outside the pack itself, but there's a lot of modeling that can be done to look at external or ambient air temperatures, compare them to cell temperatures, and provide thermal conditioning to keep battery packs within their operating range in those harsh conditions. So the danger zones for cells are, kind of rated by the cell manufacturer, and they'll tell you what the operating range is for each cell. On the cold side, there's lots of performance, so there's no really danger zone on the cold side. But on the hot side, I should say, if you try to charge a cell that's cold, that's not thermally managed, there could be a potential problem there. But typically what we're more concerned about is thermal runaway. So a cell that starts to get too hot within a pack, and then thermal propagation occurs, and you lose control of the cell. So the cell manufacturer will tell you what the safe operating limits are, and those can be set and managed at the BMS level. So the pack will minimize a discharge or charge based off of cell temperatures.
There's one more. Can this type of design be used for 12-volt batteries as well?
Yeah, I touched on that briefly, but yes, it definitely can. So it's kind of whatever the intended use is. If the 12-volt battery is being used as a starter, then just make sure you choose the right chemistry. Lithium typically doesn't have the same starting power as something like a lead acid. But if it's used for constant current as a 12-volt power supply, then absolutely, you can even build up to 80, 100 kilowatt hours at 12 volts, no problem, and have a huge amount of energy storage at low voltage. So it looks like we've got another question, which I'll read off. How are batteries designed for service? For example, remanufactured packs, or ease of removal and troubleshooting, as well as replacement with non-new packs. So, this is very dependent on the way the pack internally is constructed, and how the cells are bonded together as far as serviceability. We talked about one method that we've seen in the industry become more popular, which is, compression, or kind of like a mechanical system for connecting cells together. And what that provides is at the cell level a lot of troubleshooting, serviceability, where the pack can be deconstructed and you can service at the cell level. Otherwise, what you have is in a parallel group, like in the example in the presentation, we had 56 cells in a parallel group. If one of those cells has a problem, then you have a large amount of cells that no longer are effective inside the pack. And if they're welded together, and the pack is designed in a way that makes it hard to service, then usually the thing to do is to use the pack until it's no longer effective, and then recycle it. So, so another question about recycling. So you could talk a little bit more about recyclability in different battery pack designs. So a lot of, as long as the battery pack can be deconstructed down to the cell level, there are technologies out there in companies that are specializing in recycling lithium cells specifically. So I think the big challenge with recycling is how to deconstruct the pack and remove the cells in a way that doesn't damage the cells and they can be recycled. So lithium, as a material can be recharged. And so we're seeing a lot more like, Tesla packs that are deconstructed and the cells recycled, and you can now buy those. So there's always a way to do it, but depending on the design of the pack, it's easier or harder. So hopefully that answers that. I'm not a huge expert on recyclability, but I do know that the pack design has a huge impact on the ease of that. So it looks like we have another question about can BMS shunt cells that are over temp and others still work? So I think that's, chemistry and cell dependent. And, within a properly designed BMS, control system, you can set usable limits, for cell discharge and charge and temperature limits. So there's many ways to control that. And, but, typically packs and BMS systems are designed to work as a whole. So if you have, a section of a pack or specific cells or cell groupings that are over temp, then the discharge of the whole pack will be detuned. So and that has to do with a lot of the different things of just overall discharge to whatever you're feeding DC power to. But it's kind of the best way for me to answer that question. Awesome. Well, if there's no more questions, it was awesome to be able to to present to everybody. And I left my contact. The presentation will be shared with anybody. So please get in touch if you have any more questions after the presentation. Really appreciate you guys attending. ETTN will have their next session on August 16th on EV calibration. So Nicole added the link on the virtual education site in the chat. And so thank you very much and have a great afternoon.